All right, so we're talking about section 6.4, part 2. We're going to talk about Bernoulli equations. And Bernoulli equations are just another type of differential equation, a nonlinear differential equation, that we can make a, whoops, I guess you guys need to see what I'm writing. We can make a substitution, a clever substitution, and transform it into a linear differential equation. All right. So, our Bernoulli equation has the form y prime plus p of x y, it's coming up, equals q of x y to the n. So it's very similar to what the equation we were just working with. But this y to the n, this factor, this makes it nonlinear. If n is greater than 1. If n equals 0, then I don't have this y to the n term. Then we will just have a linear equation. If n equals 1, then the equation is separable. And by separable, what I mean is we can get all the y's on one side and all the x's on the other side and integrate both sides. So the separable differential equation is like what you worked with last year. So if n equals 1, I divide everything by y. I get y prime over y plus p of x equals q of x. You can combine the p of x and q of x together, so all the y's are together and all the x's are together, and we can integrate both sides. But if n is greater than 1, then we have a nonlinear equation. But we can make a substitution and turn it into a linear equation. So if n is greater than 1, or I guess we're going to say greater than, we could have a negative exponent. So if n is, I'm just going to say not equal to 0 or 1. N equals, not equal 0, and not equal 1. We multiply everything by 1 minus n y to the minus n. And when we do this, we will see something nice. We will see something nice happen. So let's multiply this equation. We're going to multiply through by 1 minus n, y to the minus n. So I'm going to multiply. I get 1 minus n y to the minus n y prime plus 1 minus n y to the minus n p of x y equals 1 minus n y to the minus n y prime plus 1 minus n y to the 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 q of x. And now I'm going to multiply this y to the minus n and multiply the y and simplify here, so I get 1 minus n. We're just doing some algebra here, y to the minus n y prime plus 1 minus n. Y to the minus n times y is y to the 1 minus n. P of x equals 1 minus n q of x. Everybody follow so far? Well, what is this quantity here? So think about this. I have a y to the 1 minus n here. What is this quantity compared to this quantity? What is it? The derivative. So this is y to the 1 minus n prime. Derivative of y to the 1 minus n is 1 minus n, y to the minus n, and we're saying y is some function of x, so y prime. And I still have this 1 minus n, y to the 1 minus n. P of x equals 1 minus n q of x. So I'm going to use the transformation. So this is, now we have a first order linear differential equation in a new variable. My new variable is, I'm going to let z equal y to the 1 minus n. So now I have, just rewriting this with my substitution, I have z prime plus 1 minus n. N is just some number, 1 minus n times z, p of x. And I'm going to let me rewrite that. I'm going to do p of x z equals 1 minus n q of x. So now I have a first order linear differential equation. We can apply the method that we just learned the other day to this differential equation, solve for z, and then make the substitutions equals y to the 1 minus n, and then we have our solution to our differential equation. So when we do this, our integrating factor, u of x is going to be e to the integral, e to the integral of 1 minus n p of x dx. And then we can find our solution. We say that z equals 1 over u of x, just like we did before, integral of 1 minus n. We still have this factor here, 1 minus n, q of x, u of x, dx. So when we have a Bernoulli equation, we have it in this form. We make the substitution z equals y to the 1 minus n. And we can apply this procedure, but there's a nice shortcut. We don't have to worry about all of this. We make the substitution z equals y to the 1 minus n. And then our integrating factor is 1 minus n p of x dx. And this is going to be our solution in terms of z. And then we can back substitute to get y. So we make this nice little switch of variables, and we turn it into a linear equation. So this is our key when we have a Bernoulli equation, is let z equal y to the 1 minus n. And we need to, in order to do that, we rewrite our equation in standard form where we have the y prime by itself, some function of x times y, and then we have a function of x times y to some exponent. So let's take a look at how we apply this method for the Bernoulli equation. I'll show you the little shortcut so we don't have to remember all of this stuff. So any questions on what we're doing here? So it's just another way to work with a different family of differential equations. Bernoulli equations come up often in application. Just gives us another way to work with these equations. All right, so let's look at an example. So we want to solve y prime plus 2x minus 1y equals x to the 6th y to the 3rd. So this looks a lot like the equations we've just been working with, but this makes it nonlinear. Because we have our function raised to the power of 3. So this is a Bernoulli equation. And n equals 3. So we're going to make our substitution. So we're going to say let z equal y to the 1 minus n, 1 minus 3, equals y to the minus 2. Now here's where we can save ourselves a lot of work. I'm going to find z prime. Z prime equals minus 2 y to the minus 3. And we just found this in the last equation. So what quantity is this in terms of our n's and our y's? Negative 2 is 1 minus n, and negative 3 is negative n. So this is 1 minus n y to the minus n. So I find z prime. Now I'm going to multiply the entire equation by z prime. So if I look back at our argument here, this is exactly what we did. We multiplied by 1 minus n, y to the minus n. We multiplied the entire equation by that quantity. Well, z prime gives us 1 minus n, y to the minus n. So I get, when I do that with my equation, I get minus 2 y to minus 3 y prime, minus 4 x to the minus 1 y to the minus 2, and that equals minus 2x to the 6th. You see how when we multiply through by this y term on the right hand side goes away. And I'm just going to move this, make this a little smaller. Well, this quantity is z prime. This quantity is minus 4x to the minus 1 z, and this equals minus 2x to the 6th. So now I have a linear first order differential equation with a variable z. So p of x is minus 4x to the minus 1, and my integrating factor, u of x, just going through the procedure here, so u of x is e to the integral of minus 4x to the minus 1 dx, which gives me what? What is it? So we get e to the negative 4 natural log, say absolute value of x. I can rewrite this. How do I rewrite this? So this is a place where a lot of people make mistakes when we're working with these differential equations, because this factor comes up a lot. How do I rewrite this? What is it? 4 becomes an exponent. Whoops. So this is e to the natural log absolute value of x to the minus 4th. And we argued before that we can drop the absolute value because we're multiplying through by that term all the way through. So e to the natural log of x to the minus 4 just becomes what? X to the minus 4. And I'm going to go through and I'm going to multiply by u of x. So multiply everything by u of x. And I'm multiplying this equation by u of x. So I get x to the minus 4 z prime minus 4 x to the minus 5th z equals minus 2 x squared. And I could go directly to my formula for the solution from here. I like to redo this as the derivative of a product. This is x to the minus 4z prime equals minus 2x squared. Integrate both sides, so minus x to the minus 4z equals the integral of minus 2x squared dx. Almost done. X to the minus 4z equals integral of minus 2x squared dx is what? Minus 2. I'll give it a started. X cubed. Need one more thing. Over 3 plus c. So now I can solve for z. Z equals, divide everything by x to the minus 4. So I get z equals minus 2/3 x to the 7th plus c x to the 4th. And then I can back substitute. So y to the minus 2, z was y to the minus 2 equals minus 2/3 x to the 7th plus cx to the 4th. Finish up y squared. I'm just going to take the reciprocal of both sides. And finally, y equals the square root of 1 over minus 2/3 x to the 7th plus cx to the 4th. So questions on the procedure, the process. So we're using the exact same process that we did before. We just have a few additional intermediate steps of making this substitution. Let z equal y to the 1 minus n. Find z prime and multiply by z prime. And then we transform our equation. Questions? All right. So in the homework, there are a couple of things that I want you to be aware of in the homework. there are several mixture problems where they're talking about solutions going into a tank and solutions going out of a tank. So problem number 35, which isn't on our homework, problem number 35 asks you to show that some equation is what you use for a mixture problem. Look at number 35 for mixture problems, because it gives you an equation. And you can also look at example 5 on page 427 for an example in the book of a mixture problem. They go through and solve a mixture problem there in the book. And then problem number 47 asks you to use a graphing utility to draw a slope field. I think most calculators don't. So last year we searched online and we found several places where you could draw a slope field for a differential equation. So you might need to search online for a slope field plotter. So I'm not asking you to do that one by hand. All right, so your homework is on page 430. And there are a few of these problems in this homework assignment where it just gives you a differential equation and it says solve by any method. So some of them it says it's a Bernoulli equation, some it says it's a linear equation, but some it says solve by any method. So on those you need to pick out, is it a first order linear, is it a Bernoulli equation, is it separable? So you're going to have to use what you already know to figure out the procedure. And then the mixture problems are I believe number 37 and 38.